this video, I'll go over decks, which are double-ended cues. They're pronounced like this. And I'll go over what is a deck, when to use it, as well as how to use it, and some practice using C++ and the Deque STL library. So let's first look at this example. Let's say I want to create a homework to-do list, and I want to use a double-ended cue for this. So in this list, I will have subjects that I have to complete the assignments for. At the front of the list, I have math, then I have CS, then I have bio, and let's say I have physics. So in a double-ended cue, basically the elements at the front of the list are the ones usually that I'm gonna do first. So after finishing the math homework, I will move on to CS and continue in this order, from the front to the back. Double-ended cues allow for an efficient insertion as well as removing elements from the front as well as from the back. So let's say that I just remembered that I have a history homework which is not due until next week, so I can add that to the end of the list or the back, history. And that is, in double-ended cues, that is efficient and only takes constant time. Similarly, if I have a more important homework that's due sooner than the first one, I can add that element to the front of the list. Okay, so what is a deck? It's basically a data structure, or a ADT, and it is a unique data structure since it's implemented as a linked list of arrays. So in C++, we have the STL, which is the standard template library, and Deque is basically a library that's implemented as a linked list of arrays. So this is how you basically declare. You first include the Deque library and then use the keyword Deque with the type. In this case, it's a Deque of integers that's called nums. And what linked list of arrays looks like is basically this. So this is nums, it's a Deque, and it consists of integers in this way. This is how it's implemented. Let's say we have a list of odd numbers. So we have 1, 3, 5, 7, 9, 11, and 13. And each one of these array blocks is connected to the next one. So they are linked lists that are connected together. And each one of these, instead of nodes, we have blocks of arrays. And these arrays have the same behaviors as any array, so they are indexed from 0, 1, 2, and so on. So let's say we want to get the element at index 5. So the way this works in the underlying implementation, it involves some math. So 5, we know that in the first array, it has a fixed size of 3. So 5 is greater than 3, so it basically goes into 3 one time. So that's how we know we move on to the next block. And then we get the remainder, which is 2. And that would be the index. So 0, 1, 2 of this element. And the results would return 11. Normally, if this was a connected array, the element at index 5 would be, so if we start from 0, 1, 2, this would be 3, 4, and 5. So this is the right answer. Again, it involves some math, but the way it works is like any array. And we have a few operations here that allow us to add to the beginning, which is the front, and the end, which is the back of the array. Pushback adds elements to the end of the array. So let's say we want to continue this list. We push back 15. Here's where it goes. And pop back removes the element at the end of the array. So if we pop back, then this gets removed. Push front allows us to add elements at the beginning of this deck. So the way it works is a new array is created with some size that's connected to this one. So this becomes the front array. And if we want to push front 0, then basically this is what it would look like, and it would point to the next array. Pop front removes the first element, the same way it works with pop back. And those all are very efficient, which is why decks are useful in cases where we have to remove data from the beginning or the end. So when do we use decks? Again, inserting and removing elements from the beginning or end, and it is efficient because it just takes constant time, since the way they're being inserted is just by adding a reference to this new element block. So it happens instantly without any complex time. So we also have random access, which is also constant time, because this is each one of these blocks are indexed, so we can access any element at a constant time. However, inserting, removing, and finding elements from the middle takes linear time, or O of n, because like any linked list, in case of like inserting elements, you would need to shift back all the elements or move them front. If you want to remove an element or finding, you would have to traverse the whole linked list in the worst case. So this is like when to use the decks, basically. And to further understand this, let's look at some pros and cons of these three data structures. So we know that decks are basically linked lists of arrays, and vectors, they are simply dynamic arrays, and lists are doubly linked lists. So decks are efficient when inserting and removing elements from the beginning and the end, because it only takes constant time. In the case of vectors, because they're dynamic arrays, they're only constant time with a big O of 1 when we're inserting and removing at the end, because if you want to insert in the beginning, then you would need to shift all the elements, because the way it works is like a static array, not like a linked list or how a deck would work. So with lists also, in addition to the beginning and end, inserting and removing takes big O of 1 at any known position. So if you already know the position, inserting and removing is also very efficient here. In decks, we have random access. All the elements are indexed, like how arrays works. Similarly for vectors, because they're implemented using dynamic arrays. As for lists, we have no random access and the elements are non-indexed. So accessing an element would require finding the element first and then accessing, which normally takes linear time. Decks are non-sequential in memory. Although each block is sequential, like they're built like arrays, not all the elements are sequential because these elements are not connected back to back in memory, like how regular array works, where elements are all stored one after the other. Vectors are sequential in memory, while lists or doubly linked lists are not. Decks have cheap expansion, so if we want to add or grow our deck, it's basically just adding a reference to a new block of arrays. So no need for any reallocation or copying elements. Unlike vectors, where we would need to basically reallocate and copy the elements into a whole new array with double the size, and it's more expensive in terms of space complexity, while lists are also cheap because they act in the same way as decks. So this was like some pros and cons of each one of these data structures. They all have some common features in a way, but it's important to consider these when knowing when to use which one of them and what is the best feature for each of these data structures. Now, how do we use decks? We first include this deck library, which is one of the STL standard template libraries in C++. And the way we do it is we first use this keyword. Again, we include the type, and then we give it a name. In this case, we have a deck of type int called nums. We have a few operations that are very helpful when working with decks and data. So first we have pushback, which we already saw. It is basically allows us to add elements. Let's say we have this as the front and this as the, let's call it back. So if we push back 3, we have the number 3 here. And then when we execute the next line, 3 is basically moved to the front, and now we have 5 in the back. After the following line, we have 7 in the back, and then we have 3 as the front and 5 in the middle. And once we get to this line, now we're using a different operation, which is push front. And push front adds the element, in this case it's 1, to the front of the list. So this is what our deck looks like so far. Then we have this pop front, which basically removes the element here. So we get rid of this 1, and our new front becomes 3. Now we're at pop back. It is another operation that removes the element at the back of the list. So in this case, we remove 7, and we end up with 5 as our back. We also have this insert operation, which takes 2 arguments. The first one is the iteration, and the second one is the element you want to insert. The iteration is basically the front plus how many positions you want to insert the element at. In this case, our front is 3, and then if we do 3 plus 1, we're at 5, plus 2, we're at this position, so we can add 7 back to this deck, and it becomes the back of our deck, since it's the element at the end of this deck. And erase just takes the iteration to remove the element at that position. So here we're erasing front plus 1. Front is 3, and then front plus 1 is 5, so we get rid of this 5. And in the end, we have a deck of 2 integers, 3 and 7, which 3 is our front and 7 is the back. And here, when we call nums1, which is the element at index 1, we get back 7. So here's like the operations using Deque that are involving like inserting, removing elements, and so on. This is like another way to summarize it. In this case, we have this deck of elements called D. D.push front adds 1 to the front here. Initially, this is the front, this is the back, but then we push elements to the front and the back. We pop elements from the front and the back. We could also get the size using this operation, and indexing like how we index into arrays. It works in the same way. And this is what it looks like in terms of code. So this is the same example here. Our front is, we push 3 in first, so our front becomes 3. And then once we push 1, our front becomes 1. And our back is 7, since it's the last one pushed in. And yeah, here is another example of the popping from the front and the back. And basically the beginning and the end here, we can use those by dereferencing them, because they're iterators, the beginning and end, to get the elements at the beginning and end of the deck. And we have some more operations like size, empty, which is a boolean, returns 0 or 1. And finally here, this is how you traverse a deck. So while it's not empty, so while this is true, we print out the front, and then we pop the front. So in this case, we had 1, 3, 5, 7 with 3 as our front. So once we print 1, we pop it, and then we move on to the next element. So one after the other, we end up with this.